So far, we have talked about how stack and queue work. So now we understand them, and we'll talk about a couple of applications. So first one is amazing problem. It is about a maze, a puzzle. Okay, this slide is one example of maze problems. Okay, so I think all of you are already familiar with this kind of puzzle. Okay, so in this graph, we have a starting point. On the left top, we have a start. And basically, we have to find the path from the start position to the end positions. So in these examples, the end point is the ray or the well. So we have two different problems. The first one is to find the path from start to the ray. Okay, and the second problem is to find the path from the start to the well. Okay, this kind of thing is our problem. So think about this, how to attack this problem. So we will use a stack, basically. Some of you might be wondering why this problem is so hard. Okay, then let's look at this problem from different point of view. Okay, first one is a bird's eye view. Okay, and then second one is we are in the maze. So in the left side of this slide, we have a bird eye view of this maze problem. So we have a starting point and finishing point, and we can see all this maze, from the bird eye view. So in this case, this problem is not that hard. It's kind of easy problem, but actually, the real problem is something like this. On the right side of this slide, okay, we are in the maze. So if we are in the maze, then we have no idea about the directions, or we have no idea about which path is better than the other. So it's kind of blind. So we have to choose the direction every time. Okay, so in this class, the maze problem is something like this. Computer algorithms see this problem like this in the maze. Okay, that's why this is hard. In the previous slide, we have the figures about the maze problem. Okay, that is good. Then we can enjoy this maze problem with the figure. Okay, but what about the computers? So do we have to read the image and do we have to find the path on the image? That's really difficult problem. Then what should we do? Instead of reading the figures directly, then let's build up a kind of virtual environment, virtual problem here. So we just simplify the problem with 0 and 1 here. So ones are closed and zeros are open. Okay, so we have an entrance on the left top. Okay, and then we can come to the neighbors, zero neighbors. So if it is 0, then we can go there. If it is 1, then it's closed. So we cannot go to any of ones. So from the first place, so we can go to the next zeros here on this diagonal line. Okay, and then from the second 0, which is in the bold font, from the second 0, then we have a couple of different choices. So we have 5 0 neighbors, then we have to choose. But anyway, if we are really smart, then we can choose the right one, and we can follow this path in the red color, and then we can come to this exit. So that's how we solve the problem. Okay, so basically given a maze, then and we want to find a path from entrance to exit, but basically we have to kind of transform the real problem into this computer kind of problems. Okay, so basically at each positions we will have 8 directions of movement. Okay, so it's our design, so we have 8 directions in our problem. And here is an algorithm to solve the problem. So we want to find a path. Okay, so first, let's say we are at a certain positions here, and then what should we do? So we have to follow this algorithm. First, check if the current point is exit. If the current position is exit, then that's it, right? So we solve the problem. Okay, so if that's not the case, then next, at the current positions, find all possible movements. Okay, so sometimes we have 2 possible movements, sometimes we have 3, 4, 5, sometimes we have 8 possible movements. So mark the current position not to visit again, which means, let's say we have on certain positions and then we move to the right side. And which means the current position is 0 and the right side we have 0. And when we move to the right side, then from this point, from the next point, the left side is open. But we don't have to come back to this position because we just came from that position. So we just mark the current position not to visit again. Okay, otherwise we can go back and forth infinitely. So we just mark the current positions. And next, if there is only one possible movement, then it's easy just to go to that direction. There's no other options. Okay, it's a simple problem. But if there are more than one possible movements, okay, then we have to choose. So select one direction, and then what should we do? Save the others in a repository. So if our choice is good, then we are lucky. But if our choice is not great, if our choice leads us to a dead end, then we have to come back to the other options. Okay, so we just save the other options in a repository. So it will be a stack. We'll talk about that later. But so we have to save the other options. Okay, and then if there is no possible moving, as I said before, when we follow one directions, then if we meet a dead end, so we don't have any other option, then we have to backtrack to the saved positions. So we saved all the other options, right? And then we have to backtrack to the position where we have other options, and then we will take another option. So we have to get one other option from the repository. And if the repository empty, then there's no way to exit. Okay, so if you are maybe smart, or if you are lucky, then maybe you figure out why we have a stack for this algorithm. Okay, so think about this one. So when we follow this one path, and whenever we meet other options, we push these options to our stack. And when we meet a dead end, then instead of going back to the first place, we go back to the closest other options. Okay, so we need the stack is the best data structure to handle this kind of informations. So as we've seen in the previous slide, we want to represent our maze in this way. So we have lots of ones and zeros, and the ones are closed and zeros are open. Okay, so for the m by p maze, then we have m plus 2 by p plus 2 array. Plus 2 means the walls. The outside of this maze, we have walls. So we needed plus 2 for the height and the width. Okay, and the maze is composed of road and wall. As I said, 0 is open and 1 is closed. Closed means wall and open means it is road. We can go through that positions. And each of 4 boundaries is filled with 1s to avoid boundary checking. Okay, so if we don't have these boundaries, if we don't have walls, then we have to check if this one is wall. So if this one, if when we are at the positions, then without this wall, the algorithm is a little more complicated, because am I at the edge of this maze? Then we have to check that. But instead, if we have a wall, then we don't have to check that kind of extra thing. Okay, so if the right one is wall, if the right one is 1, then it doesn't matter if this is wall or just outside the wall or inside the wall. It doesn't matter. We cannot go to that positions anyway. So with this extra wall, then we make the problem a little simpler. Okay. And the entrance is 1, 1, and exit is m, p. So this is our problem. So if you want, you can move this exit to some other place, but without loss of any generality, then this is our problem. Okay. Now let's talk about the data objects for the maze problem. First, we need the maze itself. So we have 2D array for the maze, and the size of this 2D array is row and col, row by col. And actually the row is the height plus 2 and the col is width plus 2. Okay, and if it is 0, then it is row. If it is 1, then it is wall. Okay, and then we need another 2D matrix. Okay, so for a mark for a visited position. So we need the same size of a matrix, mark, row, and col. And if it is 0, then we've never been there. If it is 1, then we've been there. And we need the repository to save a possible movement. So for this repository, we will use the stack. Why? Think about it. So we'll talk about it in the following slides, but let's think about it. Okay, so why do we need a stack? Why is the stack the best to hold these informations? So as I said before, when we have alternative options, okay, so we have let's say 3 possible directions, then we have to choose one direction, not knowing which direction is better than the others. So we have no idea. So we will choose the first one. If the first one leads us to the exit, then that's the best. But if that's not the case, then we have to try the other 2 options too. Okay, then if we have just one time selections, then it doesn't matter what kind of repository, what kind of data structure we have, it doesn't matter. But think about this one. If we choose the first directions when we have 3 options, okay, and then we move, and now we have to select one more time, right? So after selecting one direction, then after moving, then we have to choose if we have kind of alternative options. Like let's say we have 5 options now, then we have to select one of them, and then we follow that, and then now we have to choose one option out of, let's say, 2. Okay, so if we follow one path and if we meet the dead end, then we have to come back. We have to backtrack. We have to come back to the closest branch. Okay, and then we try another option. So we have to save some alternative options from the first branch. Okay, and then in the second branch we have to select one option, then we have to save another options, and then in the third branch we have to choose one direction while we save the other options. And when we meet the dead end, then we have to come back to the branch 3, not the branch 2 or branch 1. So we have to come back to the branch 3, and then we have to try another options. So instead of checking branch 1 or branch 2, we have to check the closest branch from the dead end. So the last in will be the first out, which is what the stack is good at, right? That's why we need a stack. Okay. So we have an element structure like this on the left side of the bottom. So we have an element structure, and in this structure we have a row and col and drag directions, because we need to know where we are. Okay, and also the where we are is with the row and col. So row and col will indicate where we are, and then dir, direction, indicates which direction we are looking. Okay, so that's what we have in this element structure. Okay, and then we have a stack. So as we've seen in the previous lectures, okay, the stack has a top and max size and stack array. Okay. If you want, you can have an element double pointer stack, but we might have simple implementation here. Okay. Then we need some functions. So in the previous slide, actually, I mentioned why we use the stack for the maze problem. Okay, now in this slide, we will see how we use specifically. Okay, so first, push operations. So to save possible movement, we will use push, and for backtracking, we will use pop. And whenever we move to the next positions, this will be done by assigning next coordinates to col and row. Okay, if we don't move to that positions, then we just push it, and then we will backtrack with pop operations. Okay, so I will explain that with this example. So initiate search is actually push position of entrance and backtrack. So let me explain what these operations do. Okay, so basically, so let's assume that we are here at 1,1. So this is entrance. See the left top corner, we have 0 in the green, in the bold color, bold font with underbar, underline. Okay, so this is our first positions. And then in these positions, we have one options. Okay, so the next position will be 2,2 because that is the only option. So we move to that by assigning the current position with the 3,3. Okay, so now we are 3,3. If we start from 0, then let's say this one is 2,2, sorry. So at 2,2, then how many possible directions do we have? 1, 2, 3, 4, 5. We have 5 options, but 1,1 is not counted. So we have 4 options because we just marked the 1,1. Okay, we have 4 options. Now we have to choose one of them. So in this example, so we will choose the first selection is the right one. So the right one is in the bold font with underline. So we will move to 2,3. But while we are moving to that, we will push the other green zeros into our stack. Okay, so if we meet the dead end with these current selections, then we will come back to the other options. Okay, so now we are at 2,3. Then we have 1, 2, 3, 4 options. Okay, sorry, we have 1, 2, 3, 4, 5 options, and then we will choose the right one and we will push the other options. Okay, then at 2,4, then we have 1, 2, 3, 4 options. Then at this point, we don't have the right one, so we will choose the next one. So the diagonal directions. So we'll choose that one. And the other options will be pushed into our stack. Likewise, we will just follow these directions, pushing the other options. And then look at this one. At the end of this underbar path, okay, this one is actually 1, 2, 3, 4, 5. Is it 1, 2, 3, 4? Okay, 1, 2, 3, 4. 4 comma, what's that? Anyway, big number. So anyway, the last one, it meets a dead end, right? So it has one option, but that one is actually, we've been there before, right before, so it is marked. So it's kind of a wall. It's not wall, but so that is not an option. So at these positions, we don't have any other option. So it means we meet a dead end. Okay, then what should we do? We will call pop operations. So if we pop then where is the other alternative option here? Maybe this one, the green one. Okay, so at 4 comma somethings, so we have a green one. So we'll try that one. So if this one meets a dead end too, then we'll pop. Then the next alternative option is here. In the middle of this figure, we have green ones. So we'll try that one. So it has a path. Okay, then we can find an exit following this path. Anyway, so we will follow one path. Okay, selecting one directions, and then while we are following one directions, then we push all the other options, and then we come back. Whenever we meet a dead end, then we come back with the pop operations. Okay, let's talk about the movement. So this movement slide is a little complicated, so you have to pay attention to what I'm saying, okay? So basically we have 8 directions, as you can see on this figure, okay? So from the current point, we have 8 directions, and these 8 directions can be represented by the 2 numbers, okay? So horizontal and vertical. So if the vertical is -1 and horizontal is 0, then it goes up, okay? And if the vertical is -1 and horizontal is 1, then it goes to the northeast side. Okay, likewise, with these 2 variables, then we can represent 8 directions, okay? So for the vertical, we have -1, 0, and 1. For the horizontal, we have 0, 1, and -1. So based on the combinations, we can get 8 directions. Okay, so we can use these vertical and horizontal, okay, to indicate the directions, but instead, we will use a structure, offsets. And we have an array of these offsets, and the size of this array is 8. And in this structure, we have a vertical and horizontal. So depending on this index, with this index, we will have different combination of this vertical and horizontal. For example, if the index is 0, then the vertical is -1 and horizontal is 0. So it means this direction is the north side. Okay, if the direction is 1, it means that if the index is 1, then the vertical is -1 and the horizontal is 1, which means it is pointing the northeast. Okay. Likewise, okay, let me do this one more time. If the index is 2, then the vertical is 0 and the horizontal is 1. So it points the east side. Okay. So instead of having 2 variables, we have 1 index. Okay. So that, basically the reason why we have this structure is for the implementation convenience. Okay, if you want, then you can keep this vertical and horizontals. But if we have this array of this offset structure, then it's a little more complicated. So we can use just 1 index to indicate all the directions. So if it is a 0, then it is north. If it is 5, then this is southwest, likewise. Okay, so that, let's go back to this movement statement. Next to row is row plus move dir dot vert. Okay, and then next to col is col plus move dir dot horizontal. So we have only 1 variable to indicate the direction. Perfect. Okay, let's talk about maze algorithm. Okay, for the first step, we initialize a stack to the maze entrance coordinates 1, 1 and direction to north 0. It means, for the first time, we just push 1, 1 with the direction 0 into our stack. Okay, so in our stack, we have element. Element is a structure with the row and column and the direction. Okay, so we push these numbers. Okay, and then in the next line, we check if the stack is empty. If the stack is not empty, then we iterate this loop, this while loop. So since we push it the first entrance coordinate and directions, then stack is not empty, then we go into this loop. Okay, and then we pop from the stack. Then for the first time, the row col is 1, 1 and dir is 0. Okay, And then in the next while loop, we check if dir is less than 8, because we have only 8 directions from 0 to 7. So if dir is less than 8, then still we can check that direction. Okay, and then if exit is not found, then we can keep iterating. Okay, and then in the next line, we calculate the next positions with the directions. So, we had a statement to calculate the next row and next column from the row and column. Okay, so we got these next positions, and then next line in the if statement, we check if the next position is the exit positions. If that's the case, then it is a success. Okay, and then basically we can quit. Okay, we found the exit. Okay, next, in the next if statement, we check if the maze next row, next column is a 0. If it is a 0, then it is a legal movement. Otherwise, it is illegal because it is a wall. Okay, it's closed. And at the same time, we have to check the mark array. If the mark is a 0, then we never been there. But if it is 1, then we've been there, so we don't have to check that position one more time, right? So if maze is a 0 and the mark is 0, then we can go into this block, and then first, so basically we will move to that position. We will move to the next position. So first, we will mark the next position. Okay, so we set this to the array to 1. Okay, so then in the future, we will not come back to that position again. And then next, we will push this row call dir plus 1 to the stack. So in the previous slide, I said whenever we meet the branch, then we will push all the alternative options to our stack. But we don't have to push all the options at the same time. Basically, in this implementation, when we choose one direction for the next movement, for the next positions, then we push the next direction. Okay, so row and col is the current position, and then we want to move to the next row and next col. But before moving to next row and next col, actually we push the next directions from the current position. Okay, we push the row and col dir plus 1 to the stack. So we save the next alternative option in our stack. And probably maybe this option is not the legal movement, okay, but it's okay. So we will check that later. So in this implementation, we don't check if that is alternative possible legal option or not. We don't check that. We just push that option into the stack, okay. And then we actually move to the next position with we replace row with the next row, we replace col with next col. And whenever we move to the next position, then the dir will be set to 0. So dir will point to the north all the time. Whenever we move, it starts from north. Okay. Otherwise, if this if statement is not true, then we will go to this else, where we increase dir by 1. So by increasing dir by 1, actually we will try the next direction. So actually we try all these 8 directions from north following this clockwise. Okay, so we increase the dir, and then we check the next direction, because in this the second if statement, it says next position is not legal, or next position we've been there. So in the else statement, we increase dir by 1. So we go back to the second while loop, then we check if dir is less than 8. It means still this direction is possible. Possible means we have to check. And then we will check the first if statement and the second if statement. And if the second if statement says, oh, this is not true, then we will increase dir one more time and one more time and one more time. If this dir is greater than or equal to 8, then we quit. Okay, and then we go back to the first while loop, and then if the stack is not empty, then we pop, then we get 1. Okay, this one is coming from the push. In the middle of this implementation, in the if statement, we have a push operation here. So whenever we move to the next positions, then we push the next possible option. So this is the algorithm of a maze problem, and actually this one is very close to the implementation actually. So instead of having some lines, if we use a pop and push, then it is almost implementation. Okay, now since we have an algorithm, actually we have almost implementation, then the computer can solve this complex maze problem. It's pretty confusing to us, but it's quite simple to computer.